All right, hey guys, what's going on? So today we're going to be talking a little bit more about the Hamiltonian for our Klein Gordon equation, and we're going to find out something very interesting today about the ground state energy of our Klein Gordon system. Before I get into this, again, like and subscribe. Visit my Patreon page if this kind of content is the kind of content that you're interested in. Now let's get into this. Now we're investigating the Hamiltonian for the Klein Gordon equation. So last time we sort of established the idea that the Hamiltonian is one of the most foundational concepts in field theory. Okay, you propose a Hamiltonian, you can then come forth in the world with all of the other natural consequences that come out of that Hamiltonian. So in some sense, when you propose a field theory, your Hamiltonian is what you're proposing. You can think of it like that. I like to think of it like that sometimes. So this is what we had last time, right? So we derived this in some notes that I had posted, and we're going to play with this now. Let's take a look at this. So we can rewrite this Hamiltonian like this. Now this looks weird. Why would you want to do this? Well, this, again, if you remember this, right, this came from the commutation relationship between our creation and annihilation operators. So we're replacing this right here with this, right? Because if we recall, I'll write it down here. If we recall, A and A dagger equaled 2 pi cubed like this, and these two guys, they were functions of k and k prime, right? So this here is really a dagger minus a dagger a, and then we are taking this guy here to one side and to get plus a dagger a, and that's this guy right here, right? So it's not that hard to get to this point now, or not. I don't really like saying not that hard, right? Because for some people this could be a little bit tricky to follow, and I'm trying to not make it that tricky as best as I can. But really this comes from a commutation relationship, okay? So now we have this commutation relationship, but we can notice that this and this are the same. So we bunch those up, we say that's 2 times that, and then we have this still remaining, okay? And everything still looks like it's pretty much staying the same here. But now we split up the integral, right? So we split up the integral, and we multiply by 1/2 here, right? And here, when we split up the integral here, these two guys will cancel, right? And so we get something that looks like this now. And this boils down to this, right? And this. Okay, so this guy here, so if we integrate, remember, if we integrate the delta function, at some point, the integral is 1, right? So if k prime equals k, the integral becomes 1. This really boils down to something like this, okay? And now, now we have this right here, right? This didn't change. This, I'm bringing it down, right? So bringing that down. And now, so we have this guy. Let's think about this now. This is actually very interesting. So if we recall, a dagger a, that's the number operator, right? And we have this reliance on k, right? We don't really have to think about k right now, but what we want to do is we want to say, well, okay, so this is the number operator. So if we're in the ground state, right, so when n equals 0, right, we're on the ground state. It's the number operator. It's the operator that tells you which level you're at. So if you're in the ground state, then n equals 0, right? That means that this would equal 0, right? So let's think about this. Come back, we'll come up here now. That means, that means that this goes to 0. if we're in the ground state. So in the ground state, our Hamiltonian boils down to this. Okay, let's think about this. The ground state, you can't go any lower than the ground state. Right? That's the state of lowest possible energy, or what we might think of as being no energy, because at the ground state, there's no particles. Okay, zero, you could think of it as sort of having zero energy. However, we have this term right here. Okay, I wouldn't say no particles in the ground state energy. That was sort of a misnomer. The ground energy, the ground state energy, is given by this though, because we're in ground state and we still have this term here. So I want to digress a little bit, and I want to talk about, this is just going to be a very short digression. I want to talk about a book called, I believe it's called Nothing from Something or something. It was a book by Leonard Krauss, very prominent theoretical physicist, in which he talked about how it's possible to have fluctuating energy or some sort of energy when there's nothing there at all. And for a long time, people were using this as sort of a means of disproving God or something like that. This idea that even if there's nothing, there's still something, right? There's still this ground state energy. And this is sort of a very rudimentary idea that comes from that book, which means that he sort of questions, what do you mean by nothing? When he's questioning people, like, how can something come from nothing? His question in the book was, what exactly do you mean by nothing? Do you mean just a vacuum? Do you mean the ground state of a quantum system? Right? If that's just the kind of stuff you mean, if we're being technical about it, then we use this mathematical and physical logic to get all the way down to this point of realizing that we actually have energy in the ground state. And this energy is a summation. You can look at this. This is an integral over these values of omega, right? These are angular momentum values. And we can actually get this is actually some energy in the ground state. And so what he meant by that was, we have to be a little bit more technical in what we define as nothing, right? Because here is, in some sense, a very technical definition, right? There's actually energy in the ground state. The ground state we typically associate with the word nothing, which is, again, something of an arbitrary definition. So that's just something to think about. Very interesting book. I definitely have my qualms with it, some qualms, and I definitely have some admiration for the book as well. I think it's a very good way of at least teaching some of these non-intuitive aspects of quantum field theory and quantum mechanics to students, and sort of getting them to broaden their horizons and their way of thinking about more philosophical and perhaps theological terms as well. And so there's my rant about the ground state energy and how this comes from investigating the Hamiltonian for a Klein Gordon equation. We'll be able to see this also with the Dirac equation and the Proca equation, but those are more complex, and we'll get into those shortly. I believe we're coming up on the Dirac equation in this book, and that's going to be a couple of videos on an investigation of the Dirac equation. But anyways, if you guys like this content, you can hit that subscribe, hit that like button, and you can visit my Patreon page as well, where I'll see you guys in the next one. Bye.